All right, the final lecture in this course is going to look at primarily intermolecular forces, but I do want to talk briefly about something which is called intramolecular forces, which in essence is bonding, the forces within a molecule or a chemical compound. Bonds are always stronger than intermolecular forces. Intermolecular forces are going to be attractive forces that exist between molecules, and that's primarily because of a distance thing. Now here I've got a table which kind of just gives you an idea of the different types of bonds that there are and their relative strengths. This is not an absolute. So the strongest bond is a network covalent bond, which is only found in the nonmetals of group 14, which is the carbon family. Specifically carbon, silicon, or germanium. Mainly carbon, a little bit of silicon, and even a little bit less germanium. But these three elements have the ability to bond because they have 4 valence electrons. They can bond in all 3 dimensions quite strongly and form this large network of bonds, which is the strongest type of bond that we know of. It's a specialized class of covalent bonds. Typically, covalent bonds are down here. Covalent bonds, a typical covalent bond would be a polar or nonpolar bond, and they tend to be the weakest. But this is just a specialized class found only in the carbon family. Ionic bonds tend to be the strongest of the remaining bonds. Again, there can be exceptions. Some metals can be stronger, some ionic compounds, but this is a generalization. And then metallic bonds are a little bit weaker yet. And then usually covalent bonds, polar and nonpolar bonds, are weaker yet. Okay? Now, I'm going to kind of just review this table here. This is kind of I just wrote down, and you can get this from reading the previous page, so don't please have to rewrite this. But again, bonds are stronger than IMFs. In metallic and ionic bonds, we are primarily looking at Coulombic attraction. Lattice energy is, in essence, the amount of energy it takes to break the bond. So a higher the lattice energy, the stronger the bond. There are 2 variables, just like Coulomb's law, that affects this. The higher the charge, which is Q1 and Q2, the greater the charge on the ions, the higher the lattice energy, because there's more electrical attraction. Also, size plays a factor. The size or the distance between the ions is in the denominator. So a smaller ion will be able to get closer together and therefore form a stronger bond. So in ionic compounds, if you're asked to identify which ionic compound's got the strongest bond, then you're going to look at lattice energy. You're going to look at the charges on the ions and you're going to look at their size to figure out what variable is the independent variable. Okay? For metals, it's very similar. Metals, we have the sea of electrons, which also causes there to be. So looking at metals again, with metals, we got the electron sea model. And as you can see here, here's an example of the potassium. If you have a piece of potassium metal versus a piece of calcium metal. And in an electron sea model, all of the neutral atoms of the metal, their electrons have been donated to the sea of electrons. So there are really no neutral atoms of these metals. They actually become cations, which are in essence floating around or drifting around in the sea of electrons. With metals, we can also use Coulomb's law because in both ionic and metallic bonds, it's an electrical attraction because we have charged particles. And there are 2 factors that always affect that. The distance between the particles and their size. Just like in ionic compounds, metals, the smaller they are, okay, the higher their melting points. And that's a key concept I just kind of briefly touched upon as well. A stronger bond is usually supported by the experimental evidence of a higher melting point. Or if it's a compound that tends to be a liquid, you're looking at a boiling point. Now, for an ionic compound or metal, we typically are not going to boil them because it just is unrealistic. So things that tend to be like ionic compounds and metals, we tend to focus on melting point. That is the experimental evidence that gives us support of our prediction of if it has a stronger bond or not. For an organic compound or a compound that is held together by covalent bonds, a molecule, it's typically going to be looking at boiling point. But in essence, the same idea. The higher it is, the stronger the bond. So for metals, we are looking at something which is called the electron density to surface area ratio. The better that the electrons in the sea can cover the cations, the stronger the metallic bond is. And that results in 2 ways. Either the ion can be smaller, and therefore the electrons have less surface area to cover, or Elements that donate more electrons, like calcium, donates 2 electrons per calcium atom. If there's 2 donated per one, there's going to be twice as many electrons to try to cover it. So we can see here in the model that the calcium, we have a much better surface area to electron ratio, and that causes a stronger bond. We can already predict that calcium is going to form a stronger bond than potassium. And then if we look up the melting point of each of them, we'll identify that calcium does indeed have a much higher melting point than potassium, as we predict from Coulomb's law. So for ionic compounds and metallic compounds, smaller and more charge or more electrons donated will result in a stronger bond and therefore a higher melting point. We're looking at Coulomb's law, just like looking at Coulombic attraction between the nucleus and the valence electrons. Okay? That leads us into covalent compounds. Covalent compounds are held together by fairly weak bonds. They tend to be by result of sharing electrons. So if I have 2 hydrogen atoms, what will happen is their orbitals will overlap, and then the electrons can be shared in that overlap zone, and that is a covalent bond. Now, it's the weakest bond of all of the bonds, and therefore can have very low energies for it to break. It also is indicated by these chemical compounds tend to have fairly low melting points and boiling points. They tend to be liquids or gas at room temperature. And while the bond is fairly weak, the individual molecules are held together by intermolecular forces. So I want to real quickly look at those 3 types of bonds, and here we see examples of those. And here's a table that kind of goes through all the factors I've already talked about. But in a hydrogen bonding, here we see 2 molecules of water, and a hydrogen bond occurs right here between that hydrogen and the oxygen. There could also be one here that occurs between that oxygen and hydrogen, but again, it's going to be the hydrogen that is directly bonded to an O, N, or F is attracted to another O, N, or F on a neighboring molecule, and that is a hydrogen bond. HCl cannot form a hydrogen bond because there is no hydrogen, oxygen, or fluorine. And those 3 elements are important because they're the most electronegative elements on the periodic table. HCl, the bond in HCl is a polar bond, and therefore the chlorine end of the molecule is negative, the hydrogen is positive. If another molecule comes around where the chlorine comes close to the hydrogen, there can be attraction here, because the positive end of one molecule is attracted to the negative end, and right there is a dipole-dipole force. LDFs, London dispersion forces, is the result of random movement of the electrons. If so happen when we have a hydrogen bonded to a hydrogen, this is a perfectly nonpolar bond. They share the electrons equally. But if it so happens that both electrons end up being in the same electron cloud of one of the atoms, this end of the molecule, for a very brief amount of time, ends up having a negative end and a positive end. Well, that negative end actually pushes the electrons towards the opposite end of another molecule that's nearby, and this is called an induced dipole. Induced means forced. Because of the random movement of the electrons, since this end of the molecule becomes negative, it pushes the electrons in the neighboring molecule away, and that forces this end of the molecule to become positive and this end to be negative. Now there's an attraction between these 2 hydrogens for a brief moment in time, and that's an LDF. Now, because this is so short-lived, these are not permanent dipoles. Very quickly, these electrons could bounce back, and again, now there's no dipole moment present. So just by random movement, okay, there can be these short dipoles that develop, and then they can attract to each other, but they're very short-lived. And because they're very short-lived, they're a fairly weak attraction. These other 2 have permanent dipoles, and therefore they are permanent and therefore are much stronger forces on average. However, a critical factor with LDFs is the number of them. Every bond or number of electrons, an electron cloud, can have an LDF. So when you start getting large molecules with a lot of bonds, LDFs can quickly add up and sometimes even outweigh dipole-dipole and hydrogen bonding. So when you look at IMFs, you want to look at 2 things. You want to look at the size of the molecules. If they are similar size, you want to identify what type of IMF it has. The one that has dipole-dipole forces will have a higher boiling point than the one that has just LDFs, if they are similar size. If their sizes are very different, then the one that is bigger will have more LDFs, and those larger amount of LDFs will overtrump the other types of IMFs. So look at size and then look at type of IMFs in order to answer the question. All right, so real quickly, I'd like you to pause the lecture here, and I would like you to answer questions A, B, and C utilizing IMFs to be able to explain your answers. So go ahead and pause the lecture now and do that on a separate sheet of paper, and then restart the lecture when you're ready to hear the answers. All right, I've supplied the answers here for you to look at. Whenever you're asked to explain a question like this on the national exam, it is critical that you talk about what IMF forces each substance has in your explanation. If you do not do that, you will not receive credit for your explanation. So for example, in water, you want to say that water has LDFs and it has hydrogen bonds. Again, a hydrogen bond is a specialized class of dipole-dipole forces. If you were to say LDFs, dipole-dipole forces, and hydrogen bonds, it would be perfectly acceptable too. H2S is also asymmetric, but it cannot form hydrogen bonds. It can form LDFs and dipole-dipole forces. Since hydrogen bonds are stronger than dipole-dipole forces, H2O has larger IMFs and therefore has a greater boiling point. So you want to talk about each in your explanation. So it's critical that you do this. So identify if it's symmetric or asymmetric, identify if there's an H bond at the FON, list the type of IMFs each element has, and then what's the difference that's causing the difference in the experimental evidence. Xenon, if you're looking at an element like a noble gas, xenon has a lot more electrons than neon does. And since it has a larger number of electrons, its electron cloud is larger and therefore is more polarizable. This is the word you want to get down in this explanation. The bigger an element is, the larger its electron cloud is. And when we put an electric cloud into a magnetic field, there can be a greater difference in polarity of the molecule because there can be more electrons on one side versus the other, and we can have a greater charge differential. So the more electrons we have, the more polarizable it is, and therefore it has more LDFs. Again, we talk about nonmetals. Nonmetals, the bigger it is and the more bonds it has, or the more electrons it has, the larger its LDFs, and that causes greater melting points or boiling points. For metals and ionic compounds with bonds, it's the opposite. Smaller is stronger, okay? So, key thing, if you're looking at just even an element, the one with the larger electron cloud is more polarizable and therefore has a higher melting point or boiling point than something that has less electrons. Same thing is true for the number of bonds, okay? Electron cloud. And C is very similar to A. CH4 can only form LDFs with itself, while CH3Cl can form LDFs and dipole-dipole forces. Again, make sure you explain what type of IMFs each element has, or compound, I should say. And then the additional dipole-dipole forces in CH3Cl causes a greater intermolecular forces between the molecules, and that causes a higher melting point. That's the type of explanation you need to get full credit on the national exam. If I have a chemical compound like CH4, it has 4 CH bonds. If you have another chemical compound that's CH818, this guy has way more than 10 carbon-hydrogen bonds, and even has some carbon-carbon bonds. It has a significant larger number of bonds. If there are a greater number of bonds, each bond has the ability of forming LDFs. So the more bonds you have, the more LDFs you have, and that causes a greater intermolecular force, and that's going to cause a higher melting point or a higher boiling point. Again, the experimental evidence is the melting point, boiling point that supports our prediction of who's got the higher LDFs. So for nonmetals, look at number of bonds or size or number of electrons. Okay? The intermolecular forces. If you have a chemical compound that is nonpolar, a molecule is nonpolar when it has a symmetric shape. So it's held together by covalent bonds, so they're sharing electrons as indicated by dashed lines. But first of all, in a bond, you can have polar bonds or nonpolar bonds. The only way you can have a nonpolar bond in this class is if you have an element bonded to itself because they have equal electronegativities. And therefore, they pull on the electrons with equal strength. So a nonpolar bond does not have something that's called a dipole, which is a difference in electronegativity. All other bonds between two different nonmetals will have a polar bond, and that's indicated by a little arrow. That arrow is called a dipole. A dipole indicates, it points to the more electronegative element. In this case, chlorine is more electronegative than carbon. So chlorine will pull the electrons towards its orbitals more often, and that creates a partial positive charge on the carbon and a partial negative on the chlorine, and then in essence it's forming two poles, dipole, a positive and negative pole. The greater the difference in polarity, the larger the arrow. So for example, a hydrogen-carbon arrow might be this big, but a hydrogen-fluorine arrow is going to be much, much larger. So bond polarity, you're looking at how far they're separated in the periodic table. The farther they're apart, the greater the difference in electronegativities and the more polar that bond is. There's a greater difference in electronegativities. Okay? So here we have a molecule. Now molecular polarity is looking at all of those individual bonds and seeing what happens. Well, in carbon tetrachloride, chlorine is more electronegative. So in each of these bonds, it's pulling towards the chlorine. Well, if we look at symmetry arguments, if we go look back to Algebra 2, you did something called vector addition. Well, in vector addition, this bond and this bond are pulling at equal strengths, in essence directly across from each other, and therefore they cancel. And so far with these guys. So with symmetry arguments, all of those dipoles effectively null and void cancel each other out, and we're left with something called a zero dipole moment. In your algebra class, this was called a resultant vector. When we add up all the vector arrows, it adds up to 0. There is no resultant vector left, or it has a zero dipole moment. And therefore, the molecule is nonpolar. So through symmetry arguments, all of those dipoles cancel each other out, and the molecule overall is nonpolar. Okay? If you have an asymmetric structure, now the molecule ends up being polar. Okay? Here's an example on CH2Cl2. Now, most people mistaken this guy as being symmetric, but that's because a Lewis structure does not tell us the whole picture. If I were to draw the structure using VSEPR, we'd get a tetrahedral geometry. And if I look at this tetrahedral geometry, carbon is more electronegative than the hydrogen. The chlorines are more electronegative than carbon. You'll notice if I look at all those arrows, and if I were to sum all those arrows up, if I look at the Lewis structure, it looks like these arrows might cancel each other out, and this arrow might cancel each other out. But when we actually draw the VSEPR structure, that's not the case. In the end, the molecule ends up having, if I add up these vectors, it kind of cuts right in between the chlorines. This would end up being the negative end of the molecule, and this would be the positive end of the molecule. So the key thing, keep it simple. If not all of the atoms coming off the central atom are the same, it's a polar molecule. Okay? Another way we can get asymmetry is if there are lone pairs on the central atom. Water is polar because it has lone pairs. Doesn't matter how many. If it has more than one pair, if there's a pair of lone pairs on the central atom, it is an asymmetric structure and therefore is a polar molecule. So are the atoms all coming off the same? Yes or no? And are there lone pairs? If it's asymmetric, the molecule is polar. Okay? Now, if a molecule is nonpolar, it only has one type of IMF, and that IMF is called a London dispersion force. Now, when you do the national exam, the first time you write it all the way out. And then after it, put it in parentheses LDFs. Don't start off talking about LDFs if you haven't explained or told exactly what an LDF is. A London dispersion force is the only intermolecular force found in nonpolar molecules. In polar molecules, we still have LDFs, because LDFs are present in all molecules, but we also have something called the dipole-dipole force, which literally means the positive end of one molecule is attracted to the negative end of another molecule. Those two dipoles are attracted to each other if they come together in the right shape, or I should say the right positioning. Okay? There's a third type of IMF, which is the strongest, which is called hydrogen bonding. Hydrogen bonding is actually a special type of dipole-dipole force. It's a zooped up, larger value of it, which occurs only when we have a hydrogen atom that is directly bonded to an oxygen, nitrogen, or fluorine. A way we can remember it is the hydrogen atom having any Phe. Is the H directly bonded to an O, N, or F? Here we see that these three H's, are not bonded to O, N, or F. They are not having any Phe, and therefore they cannot form hydrogen bonds. But this one hydrogen right here that is bonded to the O, if there's a direct connect to it, this can form a hydrogen bond. And that hydrogen bond occurs when another molecule of this chemical compound comes together, and that hydrogen and that oxygen will become attracted. And right here is an IMF, usually shown as a dotted line between two different molecules. The hydrogen that is very strongly bonded to the oxygen is now attracted to the other oxygen of the other molecule, and that right there, that strong attraction between those two molecules is called hydrogen bonding. Okay, so let's take a close. All right, that's pretty much the material with looking at strengths. So your homework for this part of the lecture then is for each of these examples to circle which substance you think has got either the higher melting point, or if it's gas, you could think of a higher boiling point, either one. But in essence, who's got the higher melting point, or therefore who has the stronger bond or the stronger IMF? Who is held together by stronger bonds? We look at bonds first, and if they have the same type of bonds, then we look at the IMFs between the molecules to see who's going to have the higher melting point or boiling point. And then give a reason for it. It doesn't have to be so detailed. On the FRQ for this exam, I would try to provide great detail like I just showed you in the previous problems. One last thing I want to briefly mention. So this page will be in Canvas, and I'll have the answer key for it for you to look up. The last thing with intermolecular forces is solubility with water. Okay, sodium chloride is soluble in water. Now why? Well, we have alternating sodium and chloride ions in the crystal lattice. Water dissolves sodium chloride because water is electrically attracted to the water because water is polar. And so the oxygen, which is negative part of water, gets very much attracted to the sodium ions, and then literally can take that ion and can pull it off. If you can remember back, there's something called solvation, in which the water molecule will surround these ions, causing the chemical compound to be soluble and also preventing the sodium ions and chloride ions from reprecipitating out of the solution. This is called solvation. But the intermolecular force that causes this solubility is called an ion-dipole interaction. The sodium particles are ions. They cannot form hydrogen bonds with water because it doesn't have a molecular bond. So the ion of sodium chloride is attracted to the dipole, specifically in this case, water, because of its bent nature. The oxygen part has got the negative end, and the hydrogen part's the positive end. So the dipole of water, in this case the negative dipole end of the water, is attracted to the positive sodium ions, just like reverse of that, the positive part, the hydrogen of water, is electrically attracted to the negative part of the chloride ions. So this is called an ion-dipole relationship, and it's a very or fairly strong intermolecular force that causes solubility of ionic compounds. Okay, what happens if it's not an ionic compound? Let's look at methanol. Okay, methanol is more soluble in water than CH4. Explain why. Well, what can water do? Well, we can form an intermolecular force right here between water and CH3OH. Okay, So we would say in our explanation is methanol can form hydrogen bonds with water. But again, we have to explain both. What can water form with methane? What type of attraction can occur here? And in this molecule, methane is held together by LDFs. So methane can only form LDFs, London dispersion forces. It can form LDF dipole, okay? LDF dipole IMFs with water. Therefore, CH3OH is more soluble since hydrogen bonds are a stronger IMF between the molecules than LDF dipole IMFs. So what we want to do is we want to talk about the special types of interactions they can have with water. So let's review. This is a key little table you could write down for yourself. So if it's an ionic compound and you're trying to dissolve it in water, the IMF that it can form is called an ion dipole attraction, which can be a very strong intermolecular force. If it's a polar substance with water, okay, if it can form hydrogen bonds, then that's what you're going to want to talk about. It can form hydrogen bonds with water, okay? Or it's going to form dipole intermolecular forces because both water and the polar molecule are polar to begin with. If it's a nonpolar molecule will form an LDF dipole interaction with water. The LDF is the only IMF present in the nonpolar molecule, and LDFs have the ability of forming temporary dipoles, and that'll be attracted to the permanent dipole of water, and therefore they can form LDF dipole relationships. So these are the types of IMF attractive forces that can exist between the different type of solvents you can put in water. Ionic compounds, ion dipole. Polar would be hydrogen bonds potentially, or dipole attractions with water, and nonpolar with water can form LDFs dipole relationships. Okay, the one that has greater IMFs with water will then be more soluble in water than the one that isn't. But again, just like the previous page, make sure you talk about the IMFs that each substance has with water. Okay, so that's a detailed explanation on bonding and IMFs. IMFs is a critical concept in the national exam, and if you've made it this far in the lecture, it's a critical concept that sometimes can be almost a quarter of the national exam, especially in the FRQ. So expect to see a bunch of questions, not only the multiple choice, but FRQ, that involve intermolecular forces. Again, thank you for listening, and if you have any questions, don't be afraid to reach out to me.